Hello everyone. Let's continue this chapter of the heart and see how far we can get this time. In previous discussion, we talked about how this action potential is going to go from SA node to the rest of the myocardial cell. And then we said when this action potential get to myocardial cell, this myocardial cell as a result is going to release calcium, and this calcium is going to cause cardiac muscle to contract. Today we're going to talk about the relationship between the length and tension. We talked about this one in the skeletal muscle as well, if you remember. Skeletal muscle cells, when they're at rest, they are in optimal length between 2 to 2.2, somewhere around this number. As a result, every actin and myosin, they are in perfect alignment. In the case of cardiac muscle, however, as you can see, at rest, the sarcomere is in a very short length, 1.5. As you add blood inside the ventricle, as you stretch the heart, then your sarcomere is going to get longer and longer, and until it's going to get to 2.2, which is a maximum length you can get. My point is this: the more blood comes to the heart, the more your heart is going to stretch, the better contraction will be, because as you stretch the heart and get it closer to 2.0 to 2.2, then you're going to get a perfect alignment. As a result, your heart is going to contract better because now you're using your maximum tension. So as you can see in this picture, as you increase the length of the myocardial fiber or sarcomere, your tension is going to go up. At one point, your tension is going to become plateau because you reach to a perfect alignment. After that, if you continue this curve, it's going to come down. Why is it going to come down? Because if you stretch it beyond this point, then you are staying away from the length of optimum, or it's called L maximum. So can we get to that point? No. In the normal cardiac muscle, you cannot put enough blood inside the heart to stretch it beyond LO or L maximum. That's why it's here called L maximum, because that's really a maximum physiologically. So physiologically, we can only work on this rising limb of this curve. We are not going to get to the plateau at all. So let me repeat this one more time. The difference between skeletal muscle and cardiac muscle is this: at rest, your skeletal muscle is already in the length of optimum, 2.0 to 2.2. Yet, in the case of cardiac, the length of muscle is not optimum. By adding blood inside the ventricle, you can stretch the heart. As you stretch the heart, that means you are making the sarcomere and the muscle fiber longer. You're going to reach to this length of optimum, or it's called here L maximum. As a result, the more blood you're going to put inside the ventricle, the more tension you're going to create. Why we're going to get to plateau here? Because we get to the maximum length that we can achieve. Hypothetically, if I put more blood inside the heart, after that point, you're stretching too far and this curve is going to come down. Can we do it? The answer is no. Physiologically is impossible. We saw this one in the skeletal muscle. At the resting length, as you can see here, the amount of tension you can create through the skeletal muscle is already maximum, because skeletal muscle at rest is at optimal length. However, in the case of cardiac, as you can see, my resting length is not optimum. As a result, as you increase the blood inside the heart and increase the length of the cardiac muscle, the tension is going to increase and increase. The bottom one, this one is about when you stretch the skeletal muscle. It's called passive tension, or when you stretch the cardiac muscle by putting blood inside. Now let's do something here. This is a similar curve that you saw a few minutes ago. Instead of saying here the tension of one fiber, can we replace this one with the tension of the whole muscle? So instead of considering one fiber of the muscle, we're going to consider the whole ventricle. Let's say left ventricle. Instead of considering the length of the myocardial fiber, let's think about the length of the whole ventricle. That means we're going to talk about ventricular end diastolic volume, the amount of volume that you have inside the ventricle at the end of diastole. How much blood do I have at the end of diastole before I contract? Because after diastole, systole starts. So my heart is going to get filled with the blood, and here's the end of diastole. When my heart is completely filled with blood, now my heart is ready to contract, or systole. How much blood do I have at the end of diastole? That is called ventricular end diastolic volume. So instead of talking about one fiber, we're going to talk about the whole ventricle. Instead of the tension of one fiber, I'm going to put here ventricular pressure. Instead of putting the length of one fiber, I'm going to put the volume of the blood inside the ventricle at the end of diastole. And that is going to give me very similar curve as you can see. Again, the bottom one is when you stretch the heart. Remember, stretching the heart is going to create passive tension. And this stretching the heart is going to happen during diastole. So the blue one, this one, shows you're adding blood and you're stretching the heart. So it's a passive tension. This is active tension. This is during diastole. This is during systole. There are a couple of words that I want you to know, and one is preload and the other one afterload. We also in the skeletal muscle talked about preload and afterload. What is preload? Preload is amount of volume that you have inside the heart before heart contracts. Basically, it's the end diastolic volume. How much blood I have inside the heart before my heart goes to contraction. That is called preload or end diastolic volume. When it comes to one fiber, we said that would be equal to length of that cardiac muscle. So in the case of one fiber, preload is a length of the cardiac muscle. In the case of whole ventricle, would be amount of blood you have inside the left ventricle before your heart contracts. On the other hand, we have another term, and that is called afterload. Afterload is the amount of resistance or pressure that you have after ventricle. Let's say this is your heart and this is your aorta. Now, this ventricle is supposed to push the blood inside this aorta. The amount of pressure you have inside the aorta is around 100 millimeter of mercury. If ventricle trying to push the blood inside the aorta, the pressure inside the ventricle must be more than 100 millimeter of mercury. This force that ventricle needs to overcome is called afterload. If the pressure inside the aorta goes up, then I have to create more force. That means my afterload is increasing. Therefore, we say afterload is a force that the ventricle needs to overcome, or in another word, is a total peripheral resistance, is the amount of pressure that ventricle needs to create to be able to push this blood out. When the afterload is zero, if there's no pressure inside the aorta, then your ventricle is going to contract in a maximum speed. Therefore, we say velocity of shortening of the ventricle would be maximum if there is no pressure inside the aorta. If aorta's pressure is zero, then of course your heart is going to contract as the fastest speed. As pressure inside the aorta increase, then your heart is going to contract and the velocity of shortening would be slower and slower. Now we are done with the myocardial contraction and length tension relationship. Let's now switch to another topic, and that's called cardiac output. Now think about it. Let's say this is your heart and this is the left side and this is your aorta. When this heart, when I say heart, I mean of course ventricle. When this heart is going to contract, one beat is going to send some blood out. Let's say around 70 ml. So every time your heart beats, it's going to send 70 ml out. One beat, 70 ml. Another beat, 70 ml. How many times your heart is going to beat in 1 minute? Somewhere between 60 to 100 times. So if my heart is going to send out 70 ml of blood in every beat, and it's going to beat around 60 to 100, let's say average around 75 times, that means 70 ml times 70 times in a minute, I'm pumping out almost 5 liters of blood in 1 minute. That is called cardiac output. The cardiac output is the amount of blood that you pump out in 1 minute. Therefore, the formula would be cardiac output is equal to stroke volume, how much blood you pump in one beat, that's called the stroke volume, times heart rate. If the stroke volume averages around 70 or 75 ml, if the heart rate is average about 70, then you get your cardiac output around 5 to 5.5 liters. Now, here's this very important thing that you need to consider. Our cardiac output in average is around 5 to 5.5 liters. But why is 5.5 liters? Why is not 6 liters? Why is not 9 liters? Why is not 3 liters? Well, the answer is this amount of blood, 5.5 liters, is going to give me enough oxygen that my cells can survive. I don't need more than that. Why do I have to provide more oxygen to cells when they are not using it? But if I provide less, of course my cells will die. So therefore, in a normal situation, I'm going to distribute 5.5 liters of the blood because that 5.5 liters of the blood is going to give me enough oxygen. Of course, when I do exercise, I have to provide more blood. My cardiac output should go up to provide more oxygen. But in a normal setting, we need to have 5.5 liters of the blood. So If your stroke volume goes down, if in every beat your heart cannot pump 70 ml or 75 ml blood out, if your stroke volume goes down, then your cardiac output is going to go down. That means you're not pumping enough blood. If your heart is so weak and cannot pump, then the answer is you have to increase the heart rate. On the other hand, if my stroke volume goes up, if my heart in each beat is going to pump out, let's say 100 ml, then my heart rate is going to go down. Let's take a look. We said cardiac output is equal to a stroke volume times heart rate. In a normal situation, we said we have around 175 times, let's say 175, we have around 5 liters of the cardiac output. If my stroke volume goes down to 50, then I have to increase my heart rate to achieve this 5 liter of the cardiac output. I have to increase my heart rate. If my stroke volume goes up, then I don't need to have a very high heart rate. I can bring my heart rate down to 5 liter. Why do I have to bring my heart rate down? Because again, why do I have to pump 6 or 7 liter blood out if I need only 5 liters? My body needs enough oxygen to survive. I need to keep it at 5 liters. Here's my point. My point is, if your stroke volume goes up, your heart rate goes down, and vice versa. And that is really important. If I do exercise, if I make my heart to get stronger to pump more blood out, in each beat you're going to pump more blood out, then my heart rate is going to go down. And if your heart rate goes down, that means your heart is not going to go too fast. Your heart rate is going to slow down. That means your heart is going to relax in between. And that is going to increase your longevity. So the key here is, if you do exercise, your stroke volume is going to go up. And if your stroke volume goes up, your heart rate is going to go down. And when your heart rate goes down, you are healthier. If you look at the heart rate of athletes, you can see their heart rate is in the lower end, 55, 50. If you look at people that are not really healthy, their heart rate is higher, toward 100. The key here is doing exercise is going to increase your stroke volume. When you do exercise, your heart is going to get stronger, just like any other muscle. And as a result, your heart is going to contract stronger, push more blood out. As a result, you don't need to go too fast. Your heart rate goes down. That means your heart is going to rest more. So therefore, here's the 3 things we can do to improve our stroke volume. 1, by increasing end diastolic volume. Remember, if you put more blood in your heart, if you stretch your heart, then you're going to get closer to the length of optimum. And the more you get closer to length of optimum, your heart is going to contract better. 2, if you decrease your pressure inside the aorta, if your afterload goes down, if your heart is contracting against less pressure, then the heart is going to have an easier job. And at any given length, your cardiac muscle can be strong enough to push blood. So 3 things can determine the stroke volume. 1 is how much blood you have inside the ventricle. That is going to determine the length of your cardiac muscle. The second one is the pressure inside the aorta. The lower the pressure, the heart is going to have easier time to push the blood out. And at any given time, the muscle of the heart can be strong enough to push more blood out. Let's take a look at this diagram. This is a normal one. In this diagram, as you can see, at any given volume at this moment, this person, normal person, can push out this much of the blood. It's called the stroke volume. But if your muscle is stronger, then you can push out even more. So at any given length, your muscle can be strong enough to push more blood out or less blood out. That is contractility that improves by exercise.